Okay, so for E2, we're going to sort of finish talking today. There'll be a problems sort of session on Monday on sort of all of these E1, E2, SN1, SN2. But first I want to I drew up a very quick animation of what happens with the E2, since that's what we were talking about on Friday or on Wednesday. So here's how we started out the conformation, the anti-periplanar conformation of the alkyl halide. So we've got the beta hydrogen and the leaving group anti-periplanar. We have our sp3 hybrid orbitals with the big lobe and the little lobe. And so what happens is, as the H plus leaves, and then as the leaving group, as the minus leaves, those orbitals are going to become parallel and form the double bond. So this is crude. It took me all of 5 minutes, but hopefully it'll give you a chance to see what happens. So as the hydrogen leaves, they begin to become parallel, then they're perfectly parallel, and then overlap. So the thing is, as they become parallel, the lobes become a little bit more equally spaced until they're perfectly parallel. Okay. So for those orbitals to overlap that way, they need to be parallel. And then for the hydrogen and the leaving group orbitals to basically fill out, the hydrogen has to be anti to that, because the way the orbitals are going to overlap. So that's kind of how it would look. Okay. And I think that's where we were at on Friday. Sorry, on Wednesday. Okay. Sorry. So just to review, where were we at in E2? Here's where we're at. E2. I've got two types of bases that I can use. I can use a tertiary butoxide, or I can use amide. How will you know a reaction's E2? If it involves those two bases, it's E2. So those bases have to be there. If they're not there, not E2. NH2 minus, well, the other thing we're also doing is we are deprotonating the beta hydrogen, and that beta hydrogen has to go through an anti-periplanar transition state. As far as the NH2 minus and the tertiary butoxide goes, the tertiary butoxide removes the least hindered beta hydrogen. And 9 times out of 10, that will form the less substituted double bond, but not always. So our goal here is that it's the least sterically hindered beta hydrogen. What about the NH2 minus? It produces the most stable most substituted double bond. So that's where we were at. And it took us a little bit more than 2 minutes, but that's where we're at. So now we want to look at this antiperiplanar geometry from two perspectives. One, a non-cyclic system, and then the cyclic system. And so that's what we want to look at. So we'll start with the idea of, if I gave you a starting molecule in a sawhorse, and let's say I put my hydrogen, I'll put my hydrogen here, I'll put a methyl group here, I'll put an ethyl group there, over here I'll put a CH3, a hydrogen, and a chlorine. So if I give you this molecule and I say, okay, let's write the possible products that are formed from the reaction of NH2- with this alkyl halide, and then I want to know what the major product is. So the first thing we're going to do is identify the alpha carbon that's attached to the leaving group. Then we're going to attach the beta carbon. So we're going to identify those two beta carbons. So the beta carbon is the chiral carbon on the left and the CH3 group. So is there a beta hydrogen on those beta carbons? There certainly is here, and there certainly is up here. If I erase the CH3 and make it a CH2, there's my other beta hydrogen. So I'm doing the same thing I did the other day. I'm identifying my alpha and beta carbons and then determining the beta hydrogens, because that's what the NH2- or the tertiary butoxide is going to remove. And the double bond then is going to go in between the alpha and the beta carbons. Okay. So let's write the product that is not the major product. The NH2- would come in, pull off the hydrogen attached to CH2, the pair of electrons would move here, and the chlorine would get kicked off. If I was writing the structure of that product, the left carbon did not change. So it would have the same configuration, but now I would have a double bond to the CH2, and there would be a hydrogen attached to it. So this is the minor product. As far as NH2- goes. If I wanted this to be the major product, I would use tertiary butoxide, because this is a primary hydrogen versus this being a tertiary hydrogen. So the tertiary butoxide would go after the least sterically hindered hydrogen, which would be this one. But in this case with NH2-, this is the minor product. And I oftentimes will ask you to write all the possible products and then say, circle the major one. Yes?
How do you know that the hydrogen on the bottom right there came in front from the back?
Oh, because what happened is this double bond is in the plane of the screen. Mm-hmm. There is no bold and dashed wedge.
Okay.
Because remember, a double bond, the way I write it, it's all in the plane of the screen. Mm-hmm. And so this hydrogen has to come and become in the plane.
Okay.
And then if I wanted to just show the other ones, I could write them like this. all 4 of those atoms are in the plane. Well, all 4 of the groups are in the plane.
Okay.
So it had to come forward. Okay. What?
Oh wait, no. That's
Yeah.
because 5 bonds are straight.
Yeah, I mean the only time in a double bond, I'll just add this. The only time in a double bond that you use bold and dashed wedges is if you're looking down, if you're looking like straight on the double bond and all 4 of the atoms are basically, the 2 atoms are coming towards you, the 2 dashed atoms are going away from you. So you're looking at that molecule coming in and out of the board. That's the only time you'd use bold and dashed wedges. If the double bond is going to be in the plane of the paper or plane of the paper or the screen, and the other 4 are also going to be there, there's no bold and dashed wedges. Okay. Sometimes people try and use bold and dashed wedges to indicate cis or trans, and it doesn't work that way. With a double bond, these 2 are cis, these 2 are trans. And so you don't have to use bold and dashed wedges. So there's the minor product. Now we need to write the structure of the major product. But as it stands now, this hydrogen is not anti-periplanar to the leaving group. As a matter of fact, if I'm over here looking down the carbon-carbon bond, I'm seeing this. I'm seeing my ethyl group on top. I'm seeing my methyl group over here. I'm seeing my hydrogen there. On the back, I'm seeing my CH3 group. I'm seeing the chlorine down here, and I'm seeing the hydrogen there. So that's what I'm seeing if I'm looking at the beta carbon in a Newman projection. So this hydrogen must become periplanar, must become anti-periplanar to the chlorine. Now you can do this rotation in either the sawhorse or the Newman projection, whichever one works for you. So I'll do it both ways. And I'll start with the Newman projection. So I would like to rotate the hydrogen up here. I would like to rotate the ethyl group down here. And I would like to rotate the methyl group over there. So that's going to leave me with this Newman projection. Hydrogen here, ethyl group here, methyl group here. Back carbon didn't change. And now my hydrogen that's going to be removed by the base and my leaving group are anti-periplanar. When that hydrogen leaves and the chlorine leaves, the 4 other groups, they collapse to form the sp2 hybridized planar system. Whatever's over here is going to be cis. Whatever's over here is going to be cis. So in terms of writing the final product is going to have, it's going to have the ethyl group and then the methyl group. Cis to the methyl group is the methyl group on the back carbon. Cis to the ethyl group is the hydrogen. So this would be the final product of that reaction. And the book, I guess, remembering this is, the book introduces the idea of stereoselective and stereospecific. And I'm going to ignore those terms for the time being because they don't fit well here. Okay. So the front carbon became the left, the back carbon became the right. The methyl and the 2 methyl groups are cis, and then the ethyl and the hydrogen are cis because they're on that side. Okay. So this is the only geometric isomer, the only structural isomer that would be formed. The one with the ethyl and methyl group cis is not formed. I suppose it's possible, but it's not the major product. So when we have these acyclic molecules where the stereochemistries have been shown, you will get one isomer of the double bond, but not both. Not an E2. Okay. Right, does that make sense? If I was doing this in the sawhorse, I would rotate the hydrogen up here, I would rotate the ethyl group down, and I would rotate the methyl group over there. If I draw that down here, nothing changed in the right hand carbon, but in the left carbon the hydrogen went there, the ethyl group came down to the dashed, and the methyl group came forward to the bold position.
And that's the major product because that beta hydrogen is the least there.
No, because this is the most stable product.
Okay.
NH2 minus always removes, it always forms the more stable product. It can form both, but it's always going to form the more stable one. This has 1, 2, 3 alkyl groups, and this one only had one alkyl group. So once the hydrogen is there, the base comes in, removes it, hydrogen goes here, chlorine leaves. Now in this case, the two groups that are on the bold wedges, they become cis. The two groups that are on the dashed wedges, they become cis. So depending on how you do the molecule, you will get the same answer, hopefully. But it's the two groups here that are bold that become cis, two groups that are dashed become cis. In the Newman projection, the two groups that are on one side become cis, and the two groups that are on the other side become cis.
So what you're saying by that is that like you could flip it that way and then you right then for the
As long as this structure is correct, as long as there's an ethyl methyl here and a hydrogen methyl there, and that the methyls are cis and the ethyl and the hydrogen are cis. So if you wanted to take it and rotate it so the ethyl, or so that the two methyls were on top, that's fine. But it's got to be that way. So this would then be the major product. And again, the major product has a very specific stereo isomer that's formed. If this was E2, if this was E1 with a carbocation, it wouldn't matter whether the hydrogen was up or down, but the product would be different. So you would actually get a mixture of both products. But in this case, you only get one.
Wasn't that like SN1 and SN2 also? Like with optical activity?
You sort of. Except in this case, there's no optical activity of the final product. What I guess is this is a reaction that the book calls stereospecific. And until we've really been through stereoselective, stereospecific is kind of, it's deceptive. Stereoselective reaction means that you could form two possible stereoisomers. There's two parts to this: stereo and selective. So stereoselective, the selective part means that your reaction produces two products and one of those is the major product. It's not 50-50. Okay. You can't be selective if you only have one thing to choose from. That's true in life. So you can only be selective if you make or have the possibility of making more than one product. And you actually select one, not go 50-50. Stereospecific, when you first hear of stereospecific, it's like, oh, that must be 100-0. No. Stereoselective is the term we use whether it's 50.1, 49.9, or 80-20, 90-10, or 100-0. It's selective. Specific actually means that if you change the stereochemistry of the reactant, you get a different product. And that's where SN2 and E2 are related. So stereospecific, you change the stereochemistry of the reactant, you get a different product. Think about SN2. SN2 goes by inversion of configuration. If I change from R to S, what happened to the product?
The optical sign changes.
Well, it went from S to R. It went from D to L. Well, didn't necessarily go from D to L, but it went from R to S to the other one. So if I change from R to S, I'm going to get a different product. In this case, if I changed the stereochemistry of the reactant by maybe changing a chiral center, I would get a different product. But we'll talk more about those terms. I know they're in the book. I don't know if there's any questions on them. I didn't look that far in advance. At this point, I don't think I can delete any questions, but that's what it means. So if there's any questions on there, bring them to class on Monday or Wednesday and we can go over them. But that's what stereoselective and stereospecific mean. Stereospecific is all about is really all about chirality. So if I change if the example that's usually used is biochemistry is all about stereospecificity. If I change my what's the drug that causes birth defects? The thalidomide. If I change my thalidomide from one enantiomer to the other, the reaction product changes. One from sedative to birth defects. So we have reactions that are very stereospecific in terms of their reactivities. So this is an example of the open-endedness, or the open-chained. Okay, we've got to put the hydrogen antiperiplanar to the chlorine. So here's what I need you to do. I'll give you one in the same sawhorse. Let's see. And we'll say this reaction goes NH2 minus. So here's what I need you to tell me. I need you to tell me which one of these two is the major product of this reaction. The one where we've got the ethyl, methyl hydrogen, or the one where we've got the two methyl groups being, the methyl groups are either trans or the methyl groups are cis. We'll call this one A, we'll call this one B. So which is the major product of this reaction? A or B? Okay, so I'll give you about 3 minutes to do that. And then if you, well, I'll give you 3 minutes to do that. Of course, I didn't bring my timers. So I will time you by my phone. Okay, has everybody answered? Everybody's got a chance to answer? I mean, I'm counting 25 people. Hopefully that's the same 25 responses. So 19 to 6, product A. Okay. All right, so if I'm doing this in the sawhorse projection, I've got to bring this hydrogen up here, take the ethyl group back, put the methyl group forward. That's going to put the methyl group there. It's going to put the ethyl group on the dash, and it's going to put the hydrogen there. So then when I lose the HCl, the methyl and the hydrogen are going to be cis and the ethyl group, and the methyl group would be cis. So that's A. Okay.
I say like I got that way also, but isn't there a quicker way to determine which one's the more stable one?
I don't know. A quicker way to determine what the more stable one
So
is.
it's more major product then?
Go for it.
Isn't it because A is trans, the methyls are trans, well, would be the methyls are cis, is the trans always more stable?
Whoa. You lost
The
me there.
methyls in A, aren't they trans? And then with B, they're cis. Didn't the book say like trans is always more stable than cis?
Okay. True. That's a true statement. Is it? No. In this case, the ethyl group, well, I guess. I guess the ethyl group would want to be cis to hydrogen versus being cis to a methyl group. But the stability of the product has nothing to do with whether it's the major product in E2. Okay? So here's the reason why. So remember that this is all about the antiperiplanar transition state. It's all about what the arrangement of the molecules is once this hydrogen is antiperiplanar to the chlorine. Because that geometry is locked in place, it doesn't matter whether you're forming the most or the least stable product. You're going to form the product where this geometry is formed and then is lost. Now, if it's E1, that'd be a whole other story. If it was an E1 where you could rotate around here because you have basically a carbocation, then the more stable product would be formed. But when we do E2, it's this that dictates the final product, not the stability. And you have to keep that in mind.
So A is less stable, but it's still the major product.
Maybe. The only reason I'm saying that is because I'm not exactly sure that having, I'm not sure. I'm not sure which one of these two is the most stable. The reason is because you could argue, having two methyl groups, cis is better than having an ethyl group and a methyl group cis. And the answer to that question, I don't know. What I have to do is I've got to go to the computer, and I could probably do it on my iPad, but I'd have to go to the molecule, I have to figure out what the energy of this is and what the energy of that is, and whichever one had the lowest energy would be more stable. So it's one of those things where it might be intuitive, but sometimes with energies, nothing's intuitive. And we don't have a rule per se. So A could very well be the less stable product, but it's the major product in E2. Because the product of the stability of the product has nothing to do with this transition state. Right? I drew the diagrams last time. So in E2, because this is a kinetic process, where you're looking at the transition state energy, there's really no even transition state energy to look at. I mean, it's either like this or it's nothing. So it can't form B. There would be no B at all. Only A. But that's something we have to keep in mind. If I made this an E1 reaction, I would get both. And then it'd be a question of which one's more stable. All right, so this is how we handle acyclic systems. My plan for Monday, I have lots of plans for Monday, but one of them is that I'll have some problems when you come in, these bell ringer problems, and then you can kind of go through those couple of them. So I may give you another molecule like this, except I'm not going to put the beta hydrogen on the position in the screen, and I'm not going to put. Maybe I won't put the leaving group there. Maybe I'll give you something that looks like this to start with. So that's what we'll start with on Monday, just to kind of reinforce. And then I have problems that we'll either do in groups or we can do them as a whole class. But we'll do problems with this on Monday, with the acyclic and the cyclics. But before we do cyclics, we have to talk about them. So here's the issue for the cyclics. I'm going to poll you and see what you think. Here's my alpha carbon, here's my beta carbon, here's my beta carbon, beta hydrogen A, beta hydrogen B. Okay. Bless you. So then we go NH2 minus. And my question is, now we've gone to a cyclic system, I want your thoughts on which hydrogen do you think will be removed? Which hydrogen is the NH2 minus going to remove? Is it going to remove A, or is it going to remove B? Before I tell you and before I go over it. But I think through, okay, which one of these two do I think would be removed? And since I haven't outlined it, it's not. I just want to see how good your gut feeling is. Probably. That's like T-ball. We're not keeping score. Except everybody keeps score. When I'm asking you questions like this, remember I'm just doing participation, but you should be keeping score. Right? Because if you miss something, you should go back and go, no, why did I miss that? And if he gives me another question like that, how am I going to approach it? So I'm not keeping score, but you should. All right, going once, twice. "15 A's and 9 B's. It's not a bad. That's not a bad split. Anybody want to give me a reason for choosing the way they did? Other than maybe a guess. What did you choose?
I picked A, and the only reason why I picked A was because the hydrogen was in the back on A, and B is in the front.
Okay. What did you choose?
I said A, because you have to look at the chair to see.
Okay, so we're going to have to look at the chair to see what's anti-periplanar. Yes, the hydrogen's in the back versus it being in the front. Is there any more? Can anybody help with why being in the back might be favorable than being in the front? Just a guess.
I mean, like we talked about before, like backside attack. I don't know if that has anything to do with this, but
That has nothing to do with this. What's the key phrase for this E2 reaction? Anti-periplanar. So let's go with the gruesome answer here, which is this. If I was to write out the conformation, if I'm going to write this out as a chair, here is how the molecule looks. And these are the two hydrogens that I circled, are the ones that I'm looking at. So if I'm looking down on the molecule, the chlorine is in the axial position because it's above the plane of the ring, and the other groups are placed where they are because they're either above or below the plane of the ring, depending on whether they're on bold or dashed wedges. Okay. So when I look at this structure, I see this hydrogen right here. This is hydrogen B. So can hydrogen B be removed? Why not? Because it's equatorial and hydrogen A is axial and hydrogen B is equatorial. Okay. What? True statement. Why? Again, what's my key phrase? Anti-periplanar. So what does the hydrogen have to be relative to the chlorine?
The opposite of the chlorine. Is the chlorine
I don't know. What's the chlorine? Axial. Josh, what were you going to say?
It's in the above it's in the above the chair axial position chlorine, and then the hydrogen is in below the chair.
HA. Okay.
Therefore, they're on the opposite ends.
Okay.
Opposite
So-
sides.
You're getting there. You're getting there.
They're anti-periplanar.
HA
And CL.
and Cl are anti-periplanar. Okay. If the HB and the Cl are not anti-periplanar. Now, what we should do is I should draw a Newman projection looking at this cyclohexane ring. And if I did that, it would look like this. We would have HB B here, CH3 here. On the back, we'd have chlorine. Down here, we would have the hydrogen. And then we'd have a CH2, a CH2. And then we'd have the rest of the ring, which would look like, it's getting out of control here. Okay. It would look like that. So I'm just gonna focus on this carbon, even though that's not the one that's going to be deprotonated, because I'm looking at these two carbons right here, which is this Newman projection. So if the chlorine is anti, the hydrogen that can be removed must be in this position to be anti-periplanar. It has to be in the anti position, which means that if this chlorine is above the ring, this hydrogen must be below the ring, because this hydrogen right here is above the ring. So we can actually take the anti-periplanar and say something fairly straightforward, which is that in these ring systems, the beta hydrogen must be trans to the leaving group. So HA is being removed because it's trans to the chlorine.
Now, what if you had a molecule with two hydrogens that were, like if you flipped the position of the CH3 and the HB,
Then they both would be able to be removed.
and then you just did,
And if it was NH2, the major product would be the one that was most substituted. In this case, if both HA and HB could be lost, I would get the double bond up and to the left, and I would get the double bond straight down. I'd have two major products because they would both be substituted equally. So when we're doing this E2 and cyclic systems, the hydrogens that can be removed are only the beta hydrogens that can be trans, or that are trans to the leaving group. Now, the reality is I've got to put the chlorine in an axial position, and if you're saying, well, hold on for a second, because, you know, when I took the test last week, that was not the most stable conformation. Well, I don't care about the stable conformation. What I care about is achieving that transition state. So there's nothing here that says this will occur, you know, at room temperature. I might have to put a little heat into this to do a ring flip to get the chlorine in the axial position. But the hydrogen that's being removed is going to have to be trans and also in an axial position. So again, if you can't achieve the transition state, you can't get a reaction. So we're allowed to put a little bit of heat into this. Okay. If this was E1, both those hydrogens would be able to be removed. Because once I form the carbocation, it wouldn't matter whether the hydrogen was cis or trans. So I would lose both of them. And then it would be a question of what's the major product in the reaction? The most stable one. If I'm using tertiary butoxide, my first rule is the hydrogen trans? And if it can be removed, it can be removed. Now, if there's more than one, we look at steric hindrance. But the first step in all of these reactions is the hydrogen has to be anti-periplanar. And in a ring system, it means that beta hydrogen has to be trans. Okay. So when you had your gut feeling about it being in the back and the chlorine being in the front, it was because basically the anti-periplanar means trans in a cyclohexane system.
so
this how benzene rings are formed?
Yes and no. We don't want to get the benzene rings yet. Okay. All right. So on Monday, have a couple problems to start with. If you have any questions, bring them, and then we'll do some problems, and then I'll take a look over the weekend at chapter, I guess, 11, and see what that is, because a lot of that I suspect is review of things that we've done with SN1 and SN2. And then we have 2 more topics to deal with in chapter 12 and 13, I think. All right, exam. I have the exams. I haven't posted the answer key. Maybe if I get bored in my next workshop, I will post the answers. It's a possibility, distinct possibility. For this exam, it's out of 142, but I'm going to curve it down to 135. I don't hear anybody going, that's awfully generous. Well, take a look at this. Just try and identify your errors first, and then take a look at the key. If you need, come and see me. This weekend, I'm going to be diligently working on getting these scores and all of the other scores into the grade book so that we know where we stand on Monday. If anybody's totally freaking out, wait until Monday when you get the total score, and then you can kind of see where you're at. If you want to do anything drastic. All right, so you're going to have to come to me, Colin.